Hi, welcome to the presentation for Cost-Sensitive Learning to Defer to Multiple Experts with Workload Constraints, a newly accepted paper at Transactions on Machine Learning Research. All the code using during the development of this work is available in the following repository. Let us now start with the context and motivation for our work and the contributions we propose. We all know that machine learning algorithms have been adopted in a variety of high-stakes use cases, from medicine to financial fraud detection. In some of these tasks, machine learning models can even outperform highly trained domain experts. While this may lead some to consider that human expertise is becoming obsolete, other authors choose to focus on the complementary nature of the strengths and weaknesses of machine learning models and domain experts. Domain experts are mainly limited by their processing capacity and by the fact that they can often provide inconsistent decisions. Machine learning models, however, are scalable and fast and can, on average, surpass human accuracy and are always consistent. However, the fact that they are essentially statistical models means that their worldview is limited to the training data, making them fragile to data distribution changes. This is a strength inherent to domain experts, as they can access additional information when uncertain and are capable of causal reasoning, allowing them to better deal with out-of-distribution samples. Learning to defer is a novel paradigm or type of algorithm which aims to improve human-AI collaboration by modeling both the human and the classifier's performance and then choosing to defer instances based on who's most appropriate. This can be, for example, who was most likely to be correct. However, current learning to defer research neglects key aspects of real-world settings, the first of which being limited data availability. Most of the currently proposed algorithms require every expert's prediction for every instance. Collecting this amount of data would be extremely expensive and, in some cases, unfeasible. This leads practitioners and researchers to often use simplistic simulated humans in their testing, calling into question the validity of the tests they put forward. Furthermore, the systems are trained with no awareness of human limitations. So, if an expert is consistently more accurate than others and more accurate than the machine learning model, these algorithms will choose to assign all cases to that single expert. In real scenarios, of course, human availability is limited, and not only that, it may change over time. Finally, all current research focuses on minimizing the error rate, that is, assuming that the target metric is accuracy. This is seen in recent work by the constant goal being the arrival of novel surrogate losses for the 0-1 loss. However, some scenarios may have varying error costs, such as medicine, where false positives, a false diagnosis, are less harmful than a false negative, letting someone go home sick. To tackle these issues, we propose the deferral under cost and capacity constraints framework. This system takes a set of instances, which we will be calling the decisioning queue, and the capacity constraints defined at inference time, which limit the amount of instances that can be deferred to each single human. Then, by using a machine learning classifier which models the probability that an instance belongs to a given class, and a human expertise model which estimates the probabilities of each expert being correct, we use an assigner to maximize the global probability of correctness, thus obtaining the optimal set of assignments. We also propose a new benchmark of complex, feature-dependent synthetic expert decisions in a realistic financial fraud detection scenario. This dataset is based on real-world bank account opening applications and therefore contains multiple challenges which are often not considered, but are inherent to many real-world scenarios. These can involve high-class imbalance, but most importantly, distribution shift, which is present over months of applications. We also test our system under 3 different ratios for false positive and false negative costs. Then, for each of these ratios, we create a different complex feature-dependent synthetic expert team, comprised of 9 synthetic experts. These teams are tested under 1 homogeneous and 4 variable capacity constraints. That is, assuming that each expert will be deferred the same number of instances and relaxing that restriction. The dataset we created for this benchmark is also available in the project's repository. Now, let's get into the structure of our algorithm. Our approach follows the classifier-rejector framework, similarly to previous work in rejection learning, as well as single and multi-expert learning to defer. This approach is based on the seminal work on learning with rejection by Cortes et al., and also on the 2 other works shown, which use this framework to derive consistent and base-consistent surrogate losses to the 0-1 loss for learning to defer. This approach hinges on developing a classifier responsible for automatic prediction of one of the classes, as well as a rejector, which is responsible for deciding whether the classifier should decide, and, in the multi-expert setting, to what expert the instance should be deferred. Now, for the available data, we will assume that we have a set of instances in which each instance I is comprised of a vector representing its features, the ground truth label, and the cost of misclassification incurred in the event of failing to correctly predict the label. Each instance I is also accompanied by a single prediction from an expert, which is taken out of an expert team, and the expert is identified by its ID, which goes from 1 to j. As such, we represent MJI as expert j's prediction for instance I. Our training sample then takes the form S, as shown here, meaning that we only need a single expert's prediction for each instance. In the medical case, this means that we'll have a single doctor's diagnosis for a given patient, which is a much more realistic scenario. Now let's discuss capacity constraints. Experts are limited in the amount of predictions that they can make in a window of time. As such, human capacity must then be applied over batches of instances, and not over the whole dataset at once. To define expert capacities, we split the n instance dataset into n batches, and define the vector b, in which each component denotes which batch the instance I, ranging from integers 1 to n, belongs to. We also have to define a human capacity matrix, where each element is a non-negative integer denoting the number of instances in batch B the human expert J can process. This will be crucial in the constraint programming algorithm, where these variables define the constraints. To learn the classifier and rejector, we follow a 2-stage learning approach as described by Ma et al., in which the classifier is trained separately from the rejector. To account for per instance misclassification costs, we train our classifier with a reweighted logistic loss, where the value g represents the classifier scoring function and the inverse of I represents the inverse link function, which, in the case of the logistic loss, is the sigmoid function. Minimizing this loss guarantees that the probability estimates obtained by inverting the score g will converge to the real probabilities of an instance belonging to the positive class in the limit of infinite training data. As such, if we define the classifier h as h hat, we will obtain a classifier that agrees with a Bayes optimal solution. To create our rejector, we train a human expertise model whose goal is to obtain estimates of a given expert's probability of correctness on a given instance. The human expertise model is trained using a reweighted logistic loss, which is defined as follows. This loss essentially motivates high scores if the expert is correct, and penalizes high scores if the expert is wrong. Minimizing this loss guarantees that the probabilities obtained from the scoring function converge to the probability of expert J being correct on a given instance. As such, if we define the rejector as R hat, that is, refusing to reject if the classifier is more certain than any of the humans, and deferring to one of the experts if that expert has the maximum probability of correctness. This rejector agrees with the Bayes optimal decision as well, thus proving that our method is Bayes consistent. Having defined the classifier and the rejector via the human expertise model, all that's left is to add our new component, the assigner. Via the machine learning classifier and human expertise model, the assigner receives estimates of the success of each possible assignment, and then uses constraint programming to find the best set of assignments given the capacity constraints. In short, our assigner has to decide on an assignment decision ranging from integers from 1 to j plus 2, where 1 means predicting the negative class, 2 means predicting the positive class, and j plus 2 denotes the decision to defer instance I to the jth expert. The estimated probability of an assignment leading to a correct prediction for a given instance is then given by the following expression, which uses the scoring functions trained previously. To represent the assignment decisions over a batch B comprised of NB instances, we consider a matrix of assignments A, where each element is a binary variable that denotes if instance I is effectively deferred to expert J. The optimal set of assignments is given by the following optimization problem, subject to the following constraints. The first constraint refers to human decision capacity, guaranteeing that the total number of instances deferred to a given expert is equal to the maximum number that the expert can process in said time period. The second constraint simply states that each instance must be assigned to only one decision maker. We have an example on the right where we see that the first instance was automatically predicted negative on, the second automatically predicted positive on, and the third deferred to the first expert, and so on. Having described our algorithm, we will now get into the experimental setup and the results. We chose to simulate a realistic alert review scenario, which is very common in the financial setting. The pipeline for this system is illustrated as follows. We take a set of instances which are initially triaged by an alert model to remove the clearly low-risk instances which represent automatically accepted transactions. The higher-risk instances, however, are sent to a special decisioning queue, which, along with the capacity constraints of each expert, are fed into our system to obtain optimal assignments. To train the alert model, we use months 1 to 3 of our dataset. Now, to simulate the expert decisions, we propose a following expert error model where X bar represents a normalized version of the feature vector, which is detailed in with more precision on our paper. The rest of the parameters are sampled from user-defined distributions for each expert. The vector of weights W and the value of Wm control the influence of each feature and the alert model score, as this is often a value that is shown to financial analysts. Alpha controls the magnitude of the variation induced by these features, and both betas, 0 and 1, control the base probability of a false positive and the probability of a false negative, respectively. Also, note that the signs in the equations are swapped, meaning that a region of the feature space where the expert is most likely to commit false positives will inherently have less false negatives, as presumably the expert is biased towards predicting the positive class. Having defined our expert model, we use months 4 to 7 to defer alerts randomly to expert according to their capacity constraints, creating an organic 4-month history of expert decisions. This is done with 5 different random seeds to test for variability in testing. Having trained the assignment systems on the data available, we will test them also under 5 different capacity constraints, either homogeneous or variable. Our baseline for these experiments will be Vieira et al.'s multi-expert one versus all approach, as it is the only one that is adaptable to the limited data scenario. To do so, we have to estimate the expert's probability of correctness by separating the binary classifiers. However, the classifier H will share the same structure as our method. We will also assume greedy deferral, as the one versus all approach was created only to produce optimal pointwise solutions. So, if an expert chosen by the one versus all assigner has his capacity exhausted, the system will defer to the second best expert. For our experimental scenarios, we assume that the weight for a label positive instance is 1 and the weight for a label negative is lambda, allowing us to test for different cost ratios. We also introduce variation by changing the alert model's alert rate from 5% to 15%. As we have created 5 training and 5 testing seats, this leads to a total of 25 testing conditions. We can see in the first results that classifier H can successfully model the probability that an instance is fraudulent. However, the results for the models that predict the expert correctness are much less favorable, with much higher expected calibration errors and much lower areas under the curve, due to the complexity of the used experts and the limited data availability. We show that while our approach seems to have slightly larger areas under the curve, the value of lambda has significant impact on the ranking of the algorithms in terms of calibration, demonstrating the importance of testing learning to the first systems under a wide variety of cost structures. However, it seems that despite no clear advantage being given to the ECAF on the previous results, the linear programming approach results in globally smaller misclassification costs. In every scenario, the CAF significantly outperforms the one versus all approach, and the one versus all approach even is worse than random on two of the scenarios. In this figure, we demonstrate that we can reduce the amount of training data without changing the hierarchy of the methods. To conclude, we have proposed the first constraint-aware learning to defer method that allows for inference time capacity constraints. Our method takes into account commonplace data availability restrictions and cost-sensitive scenarios. We also demonstrate that our method performs significantly better, reducing the misclassification cost by 8.4%, than the baselines in a wide array of testing scenarios, showing that there are benefits to jointly modeling the expert team. For future work, we plan on testing the addition of fairness incentives to our misclassification cost optimization method in order to study the impact the system may have in ensuring fairness. Thank you very much.